Hello, I am Pranavin Raj from Department of CSC Today I am going to explain about quadratic form analysis of potential energy matrices for stability assessment in aerospace structures. Quadratic form analysis of potential energy matrices is a foundational technique in aerospace engineering for assessing the stability of structures, especially in the context of small perturbations around equilibrium states. The method involves representing the total potential energy of a structure as a quadratic form, which allows for systematic stability assessment using eigenvalue analysis and matrix definition criteria. Introduction. It is importance of stability in aerospace structures. These energy methods provide reliable criteria for equilibrium assessment. Quadratic forms reflect structural stiffness behavior. The basic concept is in aerospace structures, the total potential energy, including strain energy and external load potential, is expanded in a Taylor series about an equilibrium configuration. The second variation, quadratic term of the total potential energy, is expressed as a quadratic form involving the potential energy matrix for a structure to be in stable equilibrium. This quadratic form must be positive definite, meaning all eigenvalues of the potential energy matrix must be positive. The quadratic forms and potential energy. Potential energy expanded near equilibrium using Taylor series. Hessian matrix represents second variation of energy, positive definiteness and stable equilibrium. Matrix definiteness tests eigenvalue criteria. All lambda greater than 0 is stable. Schlichter's criteria. All leading principles minus greater than 0. Negative or 0 eigenvalues indicate instability or bifurcation. The mathematical formulation, let U be the total potential energy and small u be the vector of generalized displacements. The second variation of U is rho u square equal to u power t ku, where k is the potential energy matrix, often called stiffness matrix in structural mechanics. Stability is ensured if k is positive definite, that is ut into ku greater than 0 for all non-zero u. The application in aerospace structures, wing panels, fuselage skins, and composite laminates evaluate behavior under in-plane compression or shear. Identify critical load conditions. The potential energy matrix K is constructed from the structural stiffness, inertia, and aerodynamic terms for aerospace applications. For dynamic stability, the matrix may be extended to include mass and damping matrices, leading to generalized eigenvalue problems for assessing oscillatory stability. The quadratic form approach is widely used in finite element models, aeroelasticity, and vibration analysis of aircraft and spacecraft structures. Bulking and geometrical stiffness. Inclusion of geometrical stiffness Kg due to preloads. Generalized eigenvalue problem K minus lambda Kg into x equal to 0. Smallest lambda gives critical bulking load. Stability assessment steps. Compute the potential energy matrix for the structure at the equilibrium point. Check the definiteness of K by examining its eigenvalues. If all eigenvalues are positive, the structure is stable. If any eigenvalue is negative, the structure is unstable. If any eigenvalue is 0, the structure is neutrally stable. It requires further investigation to find out. For nonlinear or dynamic cases, higher order terms and time-dependent matrices may be included, but the quadratic form remains central to initial stability screening. The practical considerations. The method is most effective for small perturbations and linearized systems. For complex aerospace structures, numerical methods, example finite element analysis, are used to assemble and analyze the potential energy matrix. The quadratic form approach provides a rigorous, mathematically sound basis for both static and dynamic stability assessment in aerospace engineering. This technique is essential for the design and certification of aerospace structures, ensuring they remain stable under expected operational loads and environmental conditions. The aeroelastic extensions flutter analysis involves non-conservative aerodynamic forces, state space modeling of coupled aerostructural system, and quadratic energy functions, still useful for stability. To compute eigenvalues and mode shapes, eigenvectors for stiffness matrices, you solve the eigenvalue problem defined by the matrix equation. Steps to compute eigenvalues and mode shapes. For the stiffness matrix, assemble the Clopper stiffness matrix K for the structure using finite element or analytical methods. Solve the eigenvalue equation. Use a numerical solver, example in MATLAB, Python, or specialized structural analysis software to find eigenvalues lambda and corresponding eigenvectors. Interrupt the results. Eigenvalues represent the stiffness in the direction of the corresponding mode shape. Eigenvectors show the deformation mat pattern associated with each eigenvalue. Particle implementation. In MATLAB, use the command vd eigen k, where v contains the eigenvectors, mode shapes, and d contains the eigenvalues. In Python, NumPy, use numpy.linearc.aijk for the same purpose. In structural software, most finite element packages like ANSYS, Abacus, or OpenSys have built-in eigenvalue solvers for stiffness matrices. Mode shape visualization. The eigenvectors can be plotted as nodal displacements to visualize the mode shapes of the structure. For each eigenvalue, the associated mode shape indicates how the structure deforms in that particular mode. In some special cases, if the stiffness matrix has zero eigenvalues, the structure has rigid body modes, that is, it can move without resistance in certain directions. For dynamic analysis involving mass and stiffness matrices, solve the generalized eigenvalue problem. This method is fundamental in structural dynamics, mode analysis, and stability assessment for aerospace and civil structures. The computational workflow. Assemble K and G matrices. Symmetrize matrices and compute their eigenvalues. Identify minimum eigenvalue and mode shape. Validate with FE models and analytical benchmarks. Rigid body modes correspond to motions with no strain energy, so they appear as zero or near zero eigenvalues of the global stiffness matrix and make it singular. Handling them means either constraining them approximately or treating them explicitly in the analysis workflow. What zero eigenvalues mean? A global stiffness matrix of a free or under constraint structure is positive, semi-definite, with as many zero eigenvalues as rigid body nodes, up to 6 in 3D, 3 translations, and 3 rotations. The eigenvectors associated with these zero eigenvalues span the null space of K and represent a rigid body displacement pattern with no internal strain. Eliminating rigid body modes. Apply sufficient boundary conditions so that all rigid body motions are restrained. The resulting restraint stiffness submatrix becomes positive definite and non-singular. Detecting modeling errors versus true RPMs. Intended free models should exhibit exactly the expected number of rigid body modes. Extraneous zero eigenvalues may indicate spurious zero energy modes or poor element formulation. If a supposedly constrained model still has rigid body modes, this usually signals missing or incorrect boundary conditions, excessive hinges, or unintended mechanisms that must be fixed in the model. The case study overview: panel or wing box stability under compression. That is tracking smallest eigenvalue versus load. The mode shape visualization for critical modes. Finally, the conclusion. The quadratic form analysis is a powerful stability tool which is useful for static, buckling, and aeroelastic problems. It supports safer and lighter aerospace structural design. Thank you.